about constants yesterday. Today we're going to talk about degree 1 and degree 2. Now, going over constants. Constants are ones that don't have a variable. So, like y equals 3 or f of x equals 4. They cause you to have a horizontal line, correct? That was what we said yesterday. They had a domain of XER, and their range was whatever the heck the line was. They didn't have any x-intercepts unless it was the line x equals 0, which had infinite numbers of x-intercepts. Okay? We don't deal a lot with constants, but it's just understanding what a constant is. Degree 1, we started learning these in grade 10. Actually, you kind of looked at them in grade 9 even. The graphs of 4 polynomial functions of degree 1 are shown. The graphs shown have many characteristics in common. Make a list of the common characteristics in the space below. So, what do all 4 of these lines have in common? They're straight, diagonal lines, which is true. These lines aren't horizontal and they're not vertical, right? They're diagonals. You're correct. What else is in common? What about y-intercepts? Number of y-intercepts, something like that. I'll keep going on forever. Yeah. What about y-intercepts? How many y-intercepts do each of these have? Yes. They all have one y-intercept. Is the y-intercept the same? No, but they all have one y-intercept. What about x-intercepts? How many x-intercepts do they have? One. Are all the x-intercepts the same? No. What about the domain? Yeah. Each line has one x-intercept. Yeah. Okay. What about domain? What about the domain? Its arms are going like this. Remember the horizontal line one had XER because the arrows were going in opposite directions? I feel like I am an airport attendant. Okay. What if it's going this way or this way? What would it be? Are they still going out all the way to the left and the right? Yes. So the domain is XER. Now remember the range of a constant wasn't YER, it was Y equals whatever the heck the Y was because it only went in one Y. These arrows are actually going in opposite directions out horizontally, but they're also going in opposite directions up and down too, correct? Like it's going all the way up for forever and it's going down all the way forever. So your range for these is actually YER as well. You think? All right. How does the constant term in the polynomial function relate to one of the characteristics of the graph? The constant term is the one that doesn't have a variable, correct? So this one's constant term is 2. This one's constant term is -4. This one has a constant term of 0 because it doesn't actually have one. And this one has a constant term of -4. Is there anything on these graphs that matches those numbers from what you've learned before? In grade 10, you learned there's a form y equals mx plus b, right? These are all the b's. What is the b in that equation? Yeah, the y-intercept. So if you look here, this is a +2. It has a y-intercept at +2. This one's constant is -4. It has a y-intercept at -4. This one's constant is 0, y-intercept at 0. This one's constant is -4, and it has a y-intercept at -4. So actually, the constant term of this polynomial relates to the y-intercept. The constant term is the y-intercept. Now, it's only a constant term, you guys, if there isn't brackets. If there's brackets in this equation, like say it was like y equals 2 x plus 3 plus 7 or something, and you'd have that x plus 3 in brackets, that plus 7 would not be the y-intercept, okay? The constant term only happens or occurs if the equation itself doesn't have brackets in it, okay? So all of these don't have brackets, So the constant term is the y-intercept. Now, why would that be? Whenever we're finding y-intercepts, x equals 0, correct? So in every single one of these cases, if I filled a 0 in, this would cancel and I'd be left with a 2. If I filled a 0 in, this would cancel and I'd be left with that. 0 would cancel and be left with that. 0 and cancel and be left with -4. So that's why the y-intercept is the constant. Because whenever you find the y-intercept, x equals 0, correct? And when you plug 0 into all of those, they cancel off and you're just left with the constant. Because it's the only term that doesn't have a variable on it. How can you tell from the equation of the polynomial function whether the line increases from quadrants 3 to 1 or decreases from quadrants 2 to 4? Look at the equations and see if there's anything in common that could tell you if they're increasing or decreasing. Yeah? Yeah. Anything? Yeah? Yeah, the negative is front. So the leading coefficient. If you look here, this one has a positive leading coefficient, +3 and +2. It ends positively on the right. This one has a negative leading coefficient, -0.5, and they end negative on the right. It's how they end on the right. So if you have a negative leading coefficient, you're going to want to write this down because they ask questions like this all the time. If you have a negative leading coefficient, you end down on the right. And we know that linear equations, the y equals mx plus b equations, we know that one arrow is always down and the other one's up, or the other one's down and the other one's up, right? We know that the arrows are always in opposite directions. So if we know that it's down on the right, we know then that it's up on the left. Everyone should be using a pencil or a pen and writing. If we have a positive leading coefficient, it's going to end up on the right. So the left arm, we just know where the left arm is based on the fact that it's in the opposite direction, correct? So if it's up on the right, we know that it's going to be down on the left. If it's down on the right, it's going to be up on the left, okay? So our leading coefficient tells us how it ends on the right side, on your right side, okay? The polynomial functions gx and h of x are represented graphically by parallel lines. How can we tell from the equations of the functions that this is the case? How are those both parallel lines? What tells us that they're parallel? They don't touch. What else? Look at the equations. What's similar on the h of x and g of x equations? They both have that -1/2 in front. What's that -1/2 in front? Y equals mx plus b. It's the m. What's the m always? Your slope. So these both have the same slope. They both have slope of -0.5. So they're both going to be parallel, right? Because if they have the same slope, that means they're running at the same slope, just like a ski hill. Okay? So how can we tell from the equations of the functions that this is the case? They both have a slope of -1/2. In general, what feature of the graph is represented by the leading coefficient of a polynomial function of degree 1? The leading coefficient will tell you how it ends on the right, always, to reiterate that. So if you had a negative leading coefficient, it's going to go like this. Negative leading coefficient is going to end down on the right, which means it ends up on the left. So this is quadrants 1, 2, 3, and 4. So it's from quadrant 2 to quadrant 4. If you have a positive leading coefficient, it's going to end up on the right, which means it's going to end down on the left. And this is quadrants 3 and 1. Okay. This is a little sum up. Generalize the above work to complete the following statements about all polynomial functions of degree 1 in the form f of x equals mx plus p. The shape of the graph is of what? Is a line with a slope of, in this case, m. We're just looking at this equation in particular. So in this case, it would be m. These ones back here, this would have a slope of negative a half, negative a half. This would have a slope of 2. This would have a slope of 3. But we're looking at the equation mx plus p. So this one has a slope of m. What's the domain of every single linear line? What's the domain? XER. What's the range? Element of the reals. It's the same thing. So unless it's a word problem, the domain and range of linear lines is really easy. It's just XER, YER, right? It's not hard. There is how many X-intercept? There's one X-intercept and one Y-intercept. And the Y-intercept is always the, so is the constant, right? That constant term. What's the constant term in this equation that we're looking at? B. So the Y-intercept is B. The direction of the line is determined by the value of the leading coefficient. If the leading coefficient is, in this spot, we're going to put either positive or negative. The line slopes up from 3 to 1. Does the leading coefficient have to be positive or negative? What do we put in that line? It slopes up from 3 to 1. So it ends up here. So it's positive. And if the leading coefficient is negative, it slopes down from quadrants 2 to 4. Since the graph of a polynomial function of degree 1 is a straight line, this type of function is called a linear function. Because it's a straight line. So now we're going to look at degree 2. Degree 2 you did last year, whether you were in 20-1 or 20-2, we looked at degree 2. Degree 2 are quadratics. So if you've noticed, both arrows are going up or both arrows are going down, correct? With linear, they're going in opposite directions. So with quadratics, both arrows are going down. Not at you. No, the wanderer. Okay. So we're going to look at the forms of equations for these graphs, you guys, that don't have brackets. So we're going to look at the equations that don't have brackets for now. From the list of characteristics below, circle the ones that are the same for each graph. Are the domains the same for each graph? We have arrows going out like this. Are they going to keep going out forever to the right and left? Yeah, because they have arrows going out. So they're XER. If you haven't noticed, every polynomial's domain is XER unless it's a word problem. Why would that be the case? Well, if it was a concave down parabola, let's say, and the parabola was you throwing a ball, a football gets thrown in the shape of a parabola, okay? Well, X is time. Would it go forever negative and forever positive time? Is there negative time? No, so our X would start at 0. So yes, you may say, well, it's a quadratic. It looks like it's going to keep going on forever. Yes, but word problems limit your X's and your Y's. The Y would be height, correct? Unless the football goes into the ground, it's thrown so hard that it actually goes right into the ground, it's going to be 0, okay? So your Y would be greater than 0 and your X would be greater than 0. But when it's just an equation, like this quadratic, it's going to be XER, okay? So we're going to look at these ones. They all have the same domain. Do they all have the same range? This one The lowest y I have is 10 or higher. So it will be y is greater than or equal to 10. Is this one y is greater than or equal to 10? This range? The highest mine goes here is 16, 17, 18. So it would be less than or equal to 18. Are they the same range? No. So I'm not going to circle that. Number of x-intercepts. Do these have the same number of x-intercepts? How many times does this one cross the x-axis? It doesn't. So no x-intercepts. What about this one? There's 2. What about this one? There's 1. So they have the same number of x-intercepts? No. Do they have the same number of y-intercepts? Yeah. This one crosses once. This one crosses once. This one crosses once. This one crosses once. So they have the same number of y-intercepts. How do you know the y-intercept from the equation? How do you know the y-intercept from the equation? This one has a y-intercept of 10. This one has a y-intercept of 10 as well. That's where it crosses. This one has a y-intercept of negative 8. This one has a y-intercept of negative 5. What number tells you that? The constant. Did that change between linear or quadratic? No. The constant, once again, gives you the y-intercept. And that's because when you're trying to find the y-intercept, x equals 0. When I plug a 0 in for these x's, they're going to go away. What's going to be left? Just the constant, because the constant doesn't have a variable on it. So your constant is always your y-intercept. The key thing here is, though, for this is that the equation really brutal star. The equation cannot have brackets in order for this to work. So if I look at this one, which one of these is the constant? There is no constant. I have brackets. But if I expand it out, then I have 10 is the constant. If I look at this one, which is the constant? There isn't one. But if I expand it out, negative 8 is the constant. Okay? So if I wanted the y-intercept from these ones, I'd actually have to fill a 0 in and solve for the ones with brackets. But if there is no brackets, the back number is your constant. Okay? The graphs are all parabolas. They're opening up or down, not up and down. They're either up or they're down, correct? They have one turning point, which is either a maximum or a minimum. How can you tell from the equation whether the function of the parabola opens up or down? We look at our leading coefficient again. If we have a positive leading coefficient, it's up on the right. Just what's the catch about quadratics? Their arrows are in the... Are their arrows in opposite directions or the same direction? Same. Remember linear, their arrows were in opposite directions, so if it was up on the right because it had a positive leading coefficient, it would be down on the left. So here, if it's up on the right, it's going to be up on the left because their arrows are in the same direction. So positive leading coefficient, it's up on the right, which indirectly means it's also up on the left because their arrows are in the same direction, right? Negative leading coefficient, it's down on the right because it's negative. Just like it was down on the right if it was a negative leading coefficient with linear. It didn't change. It's also going to be down on the left as well. Now, if you're a little person and you're walking along this little valley, this is the thing. People don't know which if it's a max or a min. So we're going to pretend you're a little person. Or a really large person. Whatever you are, you're walking along the valley and you get to here. Would this be the minimum of the valley or the maximum of the valley? Minimum. You're like, of course, you idiot. It's obviously the minimum. Then on the test, you write it as the maximum. So remember that when you just called me an idiot in your head and thought for sure this is a minimum. Think about it that you are the person walking along, and that's the very minimum you can go unless you got a shovel, right? Now, you're a person here, and you're climbing along, and you get up here. Where are you at? Maximum. Because you're standing on the top, and you can't go any higher, right? Now, the range can be written in the form y is less than or equal to a number, or y is greater than or equal to a number. Now, if I look at, bless you, a parabola that's concave up, and let's say that this point here is at 2 and negative 6. Say that this point is at 2 and negative 6. Is my range going to be y such that y is greater than or equal to this value, or y is less than or equal to that value? Where is the graph located? Is the rest of the graph above this value or below this value? It's above. So if the rest of this graph is above, then my range is going to be y is greater than or equal to that value. What value is it greater than or equal to? What's my lowest value here? Negative 6. For the range, I don't care what my minimum x value is. That just tells you where it occurs horizontally, right? But my lowest value is negative 6. So my range is going to be y is greater than or equal to negative 6 because the entire graph is higher than negative 6, right? So whenever you have a minimum, you get this. Now say we have a maximum instead. Say we have a graph like this. And you go into your calculator, and we're going to go in there and we're going to check. And we find the max. And the max is at 2 and 7. My range is going to be y such that y is less than or equal to 7 YER. Okay? We're not dealing with x-intercepts. We're going to deal with that tomorrow. So we're going to go and do some questions.